Hello, today we're going to be looking at the pH scale. And what we learned back a long time ago in the pH scale was that very, very low numbers, like down here, 1 and 2 and 3, would represent that of strong acids. So I'm just going to write that down here. I'm going to use a red pen, strong acid. Okay. Around this area between 4 through 6, this is generally where you have your weaker acids. All right, moving into the 7, this is where we have neutrality, neutral. And then as you move higher up the pH scale, you have your weak bases. And then higher up the scale, you have your strong bases right up in here. All right, so some examples of household products that you might have around your house. If you have stomach acid, that's hydrochloric acid. That's considered to be a strong acid. Your pH in your tummy would be pretty strong. If you happen to lose some of your stomach acid on the paint of a car, you'd find that if you left it sitting there, it would actually eat away at the clear coat and eventually destroy the paint on a car. Moving a little higher up in number, around a pH of 4, you'd find weaker acids like phosphoric acid, carbonic acid. So, for instance, people talk about, if you drink a lot of soda, it can be dangerous to the enamel on your teeth. That's where we're talking in a pH range of like 4 and 5. That would be Coca-Cola. You could also get that in seltzer. Seltzer's not as strong of an acid as the phosphoric acid found in Coca-Cola. So if we're talking about the 2 points, Coca-Cola would probably be around here, and seltzer would probably be right around there. So that's like where phosphoric acid is in relation to carbonic acid in those two particular solutions. We all know that water is neutral, and I'm going to show you water as this formula right now, especially in this chapter, and I'm going to discuss the pH scale in just a second with you. pHs of around 9 or 10, that's where we're looking at something like, for instance, cleaners inside your house. If you spray Windex on your hand, you would notice that your hand would get kind of slick. That basically is saponification, where you're taking the fat and oils from your hand and making soap. So we're talking about Windex probably being somewhere in there. I don't know where exactly it would be, but just giving you relative perspectives of the pH scale. If you were to go all the way out, like out to here, this would be Drano. Drano is very dangerous. You do not want to handle that without wearing gloves. Drano is used to clean hair clogs out of pipes. So what are we looking at with this pH scale, and what exactly does it represent? Well, the pH scale represents the actual concentration of the H plus ion. You'll notice that in pH there is an H in there. We don't call it the pOH scale, although there is one out there. It's kind of like if you're looking at DVDs against VCR tapes. Present society, if you were to have recorded media in your house that would be on some kind of material possession, the common thing that we use are DVDs more than we do VCR tapes. So same idea with pH versus pOH. There is something out there called pOH, but don't worry about it. pH reflects the H concentration. So when we're talking about the pH scale, what we're really doing is when I get a pH, for instance, of 1, when I talk about a pH of 1, I'm really talking about an H concentration of 10 to the minus 1. And 10 to the minus 1 is really 0.1 molar. If I was to move to a pH of 5, the pH of 5 gives me 10 to the minus 5 for H. And that basically is 4 zeros and then a 1 molar. That's what our H concentration would be. When we have a pH of 9, that would indicate to us that now we're moving into the basic zone. We're going to have a 10 to the minus 9 H concentration. That would have 8 zeros in the front. There's 4, 5, 6, 7, and 1. Oop, let me add a 0 there. That's what the concentration of H plus ion would be with a 10 to the minus 9. So what exists here, guys, is pretty much a seesaw relationship. Okay, when we're looking at the pH scale, the two concentrations multiplied together, if we take the H and the OH and you multiply them together, due to conductivity experiments, we have been able to realize that water conducts electricity ever so slightly. And using those conductivity numbers, we were able to come up with a number of 10 to the minus 14th. This number is stuck right here. It never ever changes. It's called a constant. And if you're given one of these two, if you're given either this or this, using this number right here, you can kind of figure out what the other number is. So in our notes, we basically said that the two, as one goes up, the other goes down. And the reason that happens is because the two numbers together have to multiply to be 10 to the minus 14th. So say I have a number like 10 to the minus 5. This exponent here for OH must be 10 to the minus 9. If this is 10 to the minus 6, then this has to be 10 to the minus 8. If this is 10 to the minus 2, this has got to be 10 to the minus 12. Now remember, our pH is coming from the digit of the H concentration. So it's very easy to figure out the pH when you have the H plus concentration. The pH in this one would be 5, the pH in this one would be 6, and the pH in this one would be 2. Notice I'm only taking the exponent of the H plus concentration. So what do I do if they give me something, for instance, say they say your pH is 12, all right? And they ask me, well, what's your H concentration? Well, that's easy to figure out because the H concentration comes from, it's basically the H concentration is just turn that pH digit into an exponent, 10 to the minus 12. If you want to know what your OH concentration is, you just have to realize that this number and this number have to add up to 14. So that's got to be 10 to the minus 2. All right. So if you're given you a pH, you know that the pH and the H have to go hand in hand. If they give you a formula, say, for instance, they give you something that's a base, and now we're going to go into more depth here. Say they give you something like 0.00001 molar NaOH. You have to first look at that formula and say to yourself, is that an acid or a base? And hopefully you realize that with this sitting right here, OH indicates to me that that is a base. All right? So that's what we really want to focus in on. So when I slide this decimal 1, 2, 3, 4, 5 places to make that a whole number, that 10 to the minus 5 is reflecting the OH concentration. Now, to figure out what the H concentration is, I have to know that these two numbers have to add up to give me 10 to the 14. That would mean that that's 10 to the minus 9. Remember, only one of these two numbers, 5 or 9, is going to be my pH. Looking at this original formula, I can see that that's a base. I know that if I'm looking at 7, that A comes before B alphabetically, and so it does also on the pH scale. A is down below 7, and B, for base, is higher than 7. So what sounds more legit? a pH of 5 for a base or a pH of 9 for a base. I'm hoping that you're going to say a pH of 9 for a base. There you go. There's your pH. And then once again, pH comes from the H concentration. So that's how you can figure this out when given any type of number. You just have to look at the formula, ask yourself, is the formula an acid or a base, or is the pH given an acid or a base? And it should make sense that the greater of the two concentrations should reflect what kind of solution you have. And hopefully that was helpful, guys.